Okay, so our previous method for solving these differential equations was by separation. Now we're going to learn the integrating factor method. So here again we have a particular form we're interested in. So the form will come from first order linear differential equations. So first order linear. What do those look like? They look like some function of x times the derivative of y with respect to x plus some other function of x times y, and that equals some function of x. For our work right now, we need to have it in the following form. So our form, we will need to divide by a sub 1 of x and get dy over dx plus a sub 0 over a sub 1 of x, which we'll just call p of x, and then times y equals g of x over a sub 1 of x. We'll just call that f of x. Okay. We require for our interval definition, we want p of x and f of x to be continuous. And in the exercises, when you're doing your work, they'll say, give the largest interval on which this general solution is defined. That's what they mean. It's the largest interval on which these guys are continuous. Okay. So they'll go through kind of the abstract version of this process, which may or may not be illuminating. One thing to be said is that you are not to memorize this form, okay, on the tests and everything. If you use this form, I will just mark it wrong. We're supposed to be memorizing the process of integrating factors, not just the solution, okay? Okay, so let's go ahead and I guess look at example 1 here, and I will kind of explain by example as to how this thing works. So we're given our differential equation. It's already in the form that we want, okay? So in particular, I'm going to identify p of x and f of x. So p of x, the thing in front of y, is -3. And in this case, f of x is equal to 0. So our interval of definition, I'll take to be -infinity to infinity. To solve the differential equation, what I need to do is form this thing called the integrating factor, which we call mu, the Greek letter mu, and it is e to the integral of p of x dx. Okay, so e to the integral in this case of -3 dx. Evaluate that integral, so I get e to the -3x. I don't need the constant, that would be overkill. Okay, this is just a means to an end, so I won't need the plus c part. Then I'm going to multiply the original differential equation that's in our form by this constant. So I'll get e to the -3x dy over dx minus 3e to the -3x y equals 0 times e to the -3x. Okay. The reason why we do this is because now that left-hand side is basically just the derivative with respect to x of mu e to the -3x times y. Okay. And then we're going to be able to integrate both sides and get our solution. Okay, so just in case you don't believe me, note if I took the derivative with respect to x of e to the -3xy, I should get this thing right here. Okay. Let's see if that works. So remind yourself I have to do implicit differentiation because I have a y term here. I'm going to have to do the product rule. Okay, so first I'm going to leave e to the -3x alone and take the derivative of y. So the derivative of y is 1 times y prime. In other words, times y prime. And then plus the derivative of e to the -3x. That's e to the -3x times the chain rule. The derivative of -3x is -3, and then times y. And then we can clean it up a little. and lo and behold, you get that thing in the red box. Okay, so it'll always work if you multiply by the integrating factor that this will result. This thing is the derivative of mu times y. Okay, so please show work. Don't just skip these steps. I need to see it. You don't need to write out the thing in red, but everything else needs to kind of be there for the test. Once you're here, you can integrate both sides with respect to x. Okay. I usually won't write the dx, but there should be a dx here. The integral of the derivative, that's one of the fundamental theorems of calculus. Those two will just kind of cancel each other out, and you'll just be left with the e to the negative 3xy. On the right-hand side, the integral of 0 is just a constant. So you'll have c. And then we want usually an explicit solution, so you can multiply both sides by e to the positive 3x. And we'll have our general solution on that interval. Okay? And it is, in fact, a general solution because of the way we've picked our p of x and f of x to be continuous. And if you want to know about that, you could read this section in the book under general solution. Okay. All right, so let's go on to example 2. In the homework, I should note they ask, are there any transient solutions? And these are solutions such that when you take the limit of the term, it goes to 0. And if you were to take the limit of ce to the 3x, it would not go to 0. Okay? It would shoot off to infinity, depending on the value of c, obviously. Okay, let's go on to example 2. Seems like we already did this one, right? It's just a little bit different in that there's a 6 on the right-hand side. It's a bit silly, right? That's the only difference, is a 6. Okay, so let's go at it. dy over dx equals, well, I guess minus 3y equals 6. Okay, so again, p of x is negative 3. F of x is 6. And so our interval of definition, we're going to make negative infinity to infinity. Our mu is going to be the same as before, e to the integral of negative 3 dx. So that'll be e to the negative 3 x. And then I need to multiply the original, the form by e to the negative 3x. And then I'm going to collapse left into the derivative of mu, which is e to the negative 3x times y. And on the right, I just have 6e to the negative 3x. Then I'm going to integrate both sides with respect to x. On the left, the integral and the derivatives kind of cancel. And you get e to the negative 3xy. On the right, you may want to u sub. You'll get a negative 1/3 constant popping out. So negative 1/3 times 6e to the negative 3x dx, or sorry, plus c. And then you can multiply both sides by e to the 3x to get y equals negative 2 times 1 plus ce to the negative 3x. Okay. Again, there are no issues with these things called transient terms, which I'll talk about here once we see one. Okay. Okay. Let's look at example 3. We're going after a general solution, x dy over dx minus 4y equals x to the 6e to the x. This is not in our form. We need to divide everything by x first. This won't work if you're not in the right form. Then you can go ahead and identify your p of x is negative 4 over x, and our p of x, or f of x, excuse me, f of x is going to be x to the 5th e to the x. Your interval of definition, you have two choices, right? Negative infinity to 0, and it's because there's division by 0 on the p of x term. You have to exclude 0 for continuity. And then 0 to infinity, you can pick either interval. Your interval will affect your mu constant, okay? We'll pick 0 to infinity as our interval of definition. So maybe this is kind of like the domain of p of x. Our interval of definition will be 0 to infinity, okay? You can pick either one. Let's see how it affects mu, okay? So mu would equal e to the integral of negative 4 over x dx. When you integrate, you get e to the negative 4 integral of 1 over x dx. And then that's e to the negative 4 ln absolute value of x. And this is where it affects your answer. On this interval from 0 to infinity, you could replace the absolute value of x with x, okay? Because the absolute value of x is equal to negative x if you're on that interval from negative infinity to 0, but then it'll equal positive x if x is greater than 0. And that's just from your piecewise definition of absolute value functions, okay? So what we're going to do is rewrite this as e to the negative 4 ln positive x. And then I'm going to move this into the exponent using the power rule, e to the ln of x to the negative 4. And then the e and the ln will cancel as inverses do, and you have x to the negative 4. Okay. Okay, but it's only because we're on this particular interval that we can replace that absolute value of x with regular x. If we pick the other interval due to like an initial condition or something like that, we would have had to use negative x. Okay, so anyways, I'm going to multiply through by x to the negative 4 now. So I get x to negative 4 dy dx minus 4x, it'll be to the negative 5th, y equals x e to the x. Okay. Now I can go ahead and collapse the left side into the derivative of mu, which is x to the negative 4 times y. On the right side I have x e to the x. Okay. Then integrate on the left, obviously the integral and the derivative again are gone. On the right, it looks like I got to do by parts, right? So u is going to be x, and dv will be my e to the x. Okay, so I got x e to the x minus the integral of e to the x dx, and we could quickly solve that integral. So x e to the x minus just plain old e to the x plus c. And that I pretty much take care of it. I need to multiply both sides by x to the 4th now. And I end up with y equals x to the 5th e to the x minus x to the 4th e to the x plus, and the constant will not absorb this variable part, so I have to leave it as c x to the 4th. Looking at this solution, and note the domain of this solution is negative infinity to infinity, but that can't be your interval of definition because we've already made this presumption that it was 0 to infinity because of this issue where we divided by 0. Okay, so that's not a peculiarity of this problem. It seems like the interval should be bigger, but it's not. Okay. Again, once you get to the homework, you're going to start worrying about transient terms. Example, whoops, there's a mistake in example 2. That should be e to the 3x because you multiply both sides by e to the 3x. Okay, so there's no transient term there. We haven't run into a transient term yet. There's no transient term in this one. It notes that 0 is a singular point when you divide it out by a sub 0. Let's see what happens in example 4, shall we? So maybe there's one of these transient solutions here. So anyways, example 4, I got x squared minus 9 times dy over dx plus xy equals 0. divide through to get it into our sort of form of the day. Get x all over x squared minus 9 times y equals 0. P of x is that x over x squared minus 9. And f of x is just 0. So there's issues continuity wherever you have division by 0. So you need to make sure x squared minus 9 on the p of x is not 0. So you get x is plus or minus 3. So the domain of p of x is from negative infinity to negative 3, union with negative 3 to the 3, and then union with 3 to infinity. The book is going to choose 3 to infinity. I'm going to go ahead and choose the middle interval just to show you what happens when you kind of have to use the one that will result in something else. Okay, so you could read the example to see what happens when you pick the outer intervals. But let's see what happens when I pick that inner interval. Okay, so it'll change your mu basically. So mu in this case, e to the integral of x over x squared minus 9. I'm going to need to do a u sub here. So u for the denominator, x squared minus 9 du is 2x dx, and then my dx is du over 2x. So I can rewrite this as e to the integral of x over u times du over 2x. That'll be e to the 1/2 integral of du over u, which will be e to the 1/2 ln absolute value of u. Back subbing, it's x squared minus 9. And here is where I'm gonna use the fact that I'm in this middle interval to rewrite it. If you think about it and go through the analysis, you'll find that the absolute value of x squared minus 9 is going to be equal to 9 minus x squared in this middle interval. So basically, if you look at like some test values, here's negative 3, here's positive 3. If you did like negative 5, you would end up with positive. If you did in here, you would end up with a negative, and here would be positive. So maybe I should do the outer parts first, right? So it's x squared minus 9 when x is less than negative 3. It'll be negative x squared minus 9 when x is in between negative 3 and 3. Oops, let's put the positive 3 on that side. And then it'll be x squared minus 9 again when x is greater than 3. Okay. So remember the definition of the absolute value, it's basically negative whatever it is when whatever is inside the absolute values is negative. And it'll be positive whatever it is, so just whatever expression it is. It'll be positive whenever that expression is greater than or equal to 0, I guess. So we have these three, intervals here where the polynomial you could see looks like this. So when it's negative in here, you have to use the negative of the expression. So you'll have a 9 minus x squared instead of x squared minus 9. So rewriting then my mu, I'll have e to the 1/2 ln of 9 minus x squared, as opposed to x squared minus 9 like they have in the book. And that's because of the choice of interval. Okay, rewriting this, it'll be e to the ln of 9 minus x squared to the 1/2. And then you can resolve this into the square root of 9 minus x squared, just using the rules of inverse functions. Okay, so that becomes our mu. We want to then multiply through the original differential equation by that thing. So I get the square root of 9 minus x squared dy over dx plus square root of 9 minus x squared times x over x squared minus 9y equals 0. Collapse that left-hand side, so that's the derivative with respect to x of mu, square root 9 minus x squared times y. And on the right-hand side, I just have 0. Integrate both sides. You get the square root 9 minus x squared y equals a constant. And then finally, you could solve for y for your general solution, c over square root 9 minus x squared. Okay, so right. And my interval of definition, I should mention then, is going to be -3 to 3. Okay. Right, so let's move on to example 5. Are they going to talk about transient? Yeah, so finally in example 5, we'll see that transient term issue that is prevalent in the homework. So, all right, this is an initial value problem. dy over dx plus y equals x, and then we have y of 0 is 4. Okay, so again, get your p of x, that's just 1 in this case, and then my f of x is x. So my interval of definition, I could just have -infinity to infinity. Get your integrating factor. Mu is e to the integral of p of x. So this should just be e to the x. Multiply by the integrating factor. X plus e to the xy equals x e to the x. Going to need my parts on that guy. Collapse. Did we already do this problem? Is that the issue? Seems like I already did this. I feel like a fool for doing it again, but then I have e to the x times y equals x e to the x. Integrate, so I get e to the x times y equals by parts. So again, I got to go u is x, dv is e to the x dx if you wish, and then it would be v is e to the x, and du is 1 dx. So it's x e to the x minus the integral of e to the x times 1 dx. And then that should give us our general solution. So x e to the x minus e to the x plus c. You can divide everything by e to the x, or in other words, multiply by e to the negative x. That'll give you y equals x minus 1 plus c all over e to the x, or c e to the negative x if you'd rather. Now you use your initial condition, and what is it, 0, 4? 0 is 4. So plugging that in, I get 4 equals x, which is now 0, minus 1 plus c all over e to the 0, which is 1. So 4 equals -1 plus c, so c equals 5. And so our particular solution, y equals x minus 1 plus 5 all over e to the x. Okay, so this time we actually get a transient solution, and it's this thing. Because if you took the limit as x goes to infinity of that, you'll have the form L over infinity. If you have some constant over something getting really, really big, it's going to go to 0. So anything of that type form is going to go to 0, like the limit as x goes to infinity of c all over e to the 20x. You're going to just say that's a transient term because that denominator is going to get huge. So assuming that c is not 0. So there'll be transient terms in each sort of question, and yeah, it's sometimes a little tricky, like in number 8, you can see my solution there is e to the x all over 2x squared plus c all over x squared e to the x. The first term is not a transient term, and it's because the numerator is growing faster than the denominator. So to evaluate this limit, you'd have to do L'Hopital's, because right now it's infinity over infinity form. So you would do L'Hopital's, in other words, take the derivative of the top, that's e to the x, take the derivative of the bottom, that's 4x. That's still infinity over infinity, so you do L'Hopital's again. And you would just get e to the x over 4, which would shoot off to infinity. So it's getting bigger and bigger and bigger. It's not going to 0. It's not going to vanish. So therefore, it must be not transient. Okay, and compare that to this guy where the denominator is just going to be getting huge and that numerator is just going to be some number L, supposing that C is not 0. Okay, and in that case, you're going to have L over infinity. That will go to 0, so that would be transient. So this is transient, but the other guy is not. Okay. Usually you could tell which one is going to be transient. So this one doesn't have any transient terms because you'll have something, a constant on top, and then something variable in the denominator. So in this case, you might have to do L'Hopital's, but at the end of the day, the e to the x in the denominator is going to just go so much faster than 4x squared that it's going to be transient. Right? These are both transient. This is not transient, not transient. This is also not transient because that e to the 6x would actually go to the numerator. But they're not even asking for that anyway, so it doesn't matter. Okay, so anyways, hopefully that makes sense. Piecewise definitions. Okay, so these are basically two problems for the price of one. So we have this differential equation. Y of 0 equals 0, and f of x is two things, 1 and 0. Is that a mistake? They made a mistake. Are you serial? They made a mistake in the book. It should be f of x on this side. Okay, so I have 0 less than or equal to x less than or equal to 1, and then x greater than 1 here. So what you're going to do is solve each one of these versions. So you have dy over dx plus y equals 1. You're going to solve that. And then you're going to turn around and solve this. Okay. You'll use the initial value to solve for the constant and the first problem to get your particular solution. And then for the second problem, you want the two answers to be continuous. Okay. So what you do is kind of use that fact in order to figure out the constant in your second answer. Okay. Okay, so let's go ahead and see how this is done. P of x and f of x are both continuous. P of x is 1, f of x is 1, so negative infinity to infinity would be our interval of definition. It's not really going to make a difference here, but mu is going to be e to the integral of 1 dx, which will just be e to the x, so multiply through by that. Collapse the thing, so you get the derivative with respect to x times e to the x times y, e to the x, integrate, and you get e to the x y equals e to the x plus c. Get the explicit solution, c e to the negative x, and then we could use the initial value to solve for c. Okay, so y of 0 is 0. So plugging in 0 for y equals 1 plus c. E to the 0 is just 1. So c will be negative 1. And so one piece of our solution for our final answer is going to be 1 minus e to the negative x. Okay, and that will be on the interval from 0 to 1. Okay, so let's get the other part. Again, my integrating factor is just going to be e to the x. Okay, so I'll end up with e to the x dy over dx plus e to the xy equals 0. Collapse it. Integrate both sides. Get your explicit solution, and there we got it. Okay. Technically, that would represent a whole bunch of answers, but we want our answer to be continuous on this interval. So we don't want like a big gap in between the two answers. Okay, so we want them to connect. Even if it's not differentiable, we still want them to be, want our solution to be continuous. So what we do is kind of see what this is at 1. So y of 1, we want to equal 1 minus e to the negative 1. Okay? In other words, 1 minus 1 over e. So we take this as kind of an initial condition for the second piece right here. Okay? So I'm going to write y as 1 minus 1 over e, and then replace x with 1. So I get ce to the negative 1. Okay? And then I'm going to solve for c. So just multiply both sides by e to the positive 1. And I'll get e minus 1 for my constant. And now I can write up my second piece of my solution with this constant. So it'll be e minus 1 for c, and then e to the negative x when x is greater than 1. Okay. And that will be continuous on the interval from 0 to infinity. All right. One thing, they introduce the error functions. Sometimes when you're doing your integrals, like in Wolfram or something, you'll see this weird function called ERF. Usually when you're integrating something like e to the negative x squared, which would kind of come up in probability when you're dealing with normal distributions. The output will have an ERF function. You see it right there, ERF. So we can define the integral of e to the negative x squared dx as 1/2 square root pi ERF of x. Okay. I don't think it comes up in the homework, but they do use it to explain their answer in example 7. So let's see if we can cruise through that one real quick, and then we'll look at some WebAssign stuff. I think seems like a good idea. Okay, so example 7, our differential equation dy all over dx minus 2xy equals 2, and y of 0 equals 1. This is one, I guess we can embed the, well, let's just not get too carried away. Let's look for mu first. So mu equals e to the integral of the negative 2x, that's at p of x. And this will be e to the negative x squared, 2x squared over 2, which is negative x squared. So after all is said and done, you'll get the derivative of mu times y, and of course that'll equal 2e to the negative x squared. Then we can integrate both sides, and again, with regards to solutions in terms of integrals, we can embed the particular solution to the integrals, like that. And so on the left-hand side, we'll have e to the negative x squared, y of x, minus y of 0. And then on the right-hand side, we'll have just that integral. There's not anything we do. We'll just put it in dummy terms, right? Replace that x with a t. So e to negative t squared dt from 0 to x. Okay. And that thing's going to be our ERF. We'll see that ERF function kind of pan out in there. So anyways, we have y e to the negative x squared minus y of 0, we said is 1, so just e to the negative x squared equals 2 integral 0 to x e to the negative t squared dt. So you could divide through everything or multiply everything by e to the positive x squared. You get y minus 1 equals 2e to the positive x squared integral 0 to x e to the negative t squared dt. and then move the 1 over and replace the function as an IRF. Seems like I screwed something up. Y of 0. So it's probably back here when I was fooling around with this stuff. I didn't do that right. Somehow I didn't embed it right, so I'm not used to doing that. But it should just be like this. So the e to the negative x squared yx, and then minus your initial condition. Okay, sorry about that. And then I'm not going to ask you to do this on a test or anything. I think it's just interesting to see how that where that IRF thing pops up. Anyways, so this should be 1. And then if you multiply through by e to the positive x squared, this will be e to the positive x squared. And then y will equal, you can factor out the e to the positive x squared. You get 1 plus 2, and then you kind of got to rewrite it so it's square root, whoops, wrong way around. We need the 2 on the inside and the square root of pi out here, like this. And then integral, and then that would be your IRF thing, integral e to negative 2 squared from 0 to x dt. Okay. So y would equal e to the x squared times 1 plus square root pi IRF of x. Okay, but like I said, those aren't going to pop up in the homework. Speaking of the homework, let's kind of look in there and see if there's anything crazy. These last 2 problems are the ones where you're solving, they're piecewise. So you got to make them continuous. And they're all pretty. Oh, let's look at that one, that number 16. So it's like Kirkhoff's law. So Ri equals the press voltage, I of 0 is I sub 0, and we got a bunch of constants. Okay, so first I got to get it into our form of the day by dividing by L. So we get plus R over Li equals E over L. I is like y, so our mu value is going to be e to the integral of r over L dt. So you get e to the r over L t, and then multiply through and collapse it. You get the derivative with respect to t of e to the r over L t times I. On the right hand side, you get e over L times e to the r over L t. Excuse me, integrate both sides. So you get e to the r over L t I. On the right hand side, you may need a u sub if you wish for the r over L t. And du would be r over L dt. And dt would be L over r du. So pulling out the e over L, the integral of e to the u times L over r du, presuming that we integrate with respect to t like that. And then I get e to the r over L t I equals e over L, and then times L over r, you can pull that out. And then the integral of e to the u is just e to the u, back summing e to the r over L t. And then plus integration constant. Divide everything by e to the r over Lt. You get I equaling, some cancellation there, e over r plus c e to the negative r over Lt. And then use the initial condition to get your final answer, noting then I of 0 is I sub 0. So I sub 0 would equal e over r plus c e to the 0, which would just be 1. So c equals I sub 0 minus e over r, and then back sub that in, and you get your answer that you see over here. Okay. The interval of definition, note that p of x and f of x are both constants, so there's no issue with division by 0 or anything. Assuming L is not going to be 0, you're okay. So finally then, my interval of definition is -infinity to infinity. Okay. So I guess we could back sub just for completion. And I is -infinity to infinity. Okay, so that's good enough. Hopefully that will get you through homework. And as usual, thank you for watching, and we'll see you next time.